Hey team. Okay, today we're going to be talking about energetics and we're going to be starting with metabolism. You may have learned that metabolism has like two components, which is anabolism and catabolism. So we're gonna talk about what are those things, what are the differences, and then we're gonna talk about balancing redox reactions, how those work, why they work. It's gonna be so much fun. Okay, energetics. So yeah, we're starting with metabolism, which is composed of catabolism and anabolism. So catabolism is energy generation, meaning you're breaking down stuff with like stored energy and taking the energy from it. So you have a substrate that has some energy, like of course glucose, our classic example, and you turn it into products. And that reaction releases energy. Okay. So catabolism, energy generation, right? We can write that. And you can use that to, for example, make ATP, strengthen the PMF, the proton motive force. Your proton gradient. But also that energy can go to anabolism, which is energy consumption. But it's making stuff. So it uses that energy to take monomers and turn them into something. So I'm going to say like macromolecules. That's a classic, you need your biomolecules, other products. So these are useful for the cell. So we use that energy that we got from catabolism. I'm just going to draw it like that. Like it's going into the reaction to turn monomers into something useful for the cell through biosynthesis. So anabolism is energy use. Okay, but how do we get energy from a compound? How do we have a substrate releasing energy as it's turning into products? So I'm going to say, where does the energy come from? So for example, in glucose, you break bonds and you process a product, and eventually that causes you to increase your energy, and you can like power a proton gradient and stuff. So how do we do that? So every single cellular process is powered by redox reactions. Redox meaning reduction oxidation, which you probably learned about in general chem. I'm just going to say reactions. And in general chemistry, we learned about different elements and compounds of those elements having different chemical properties. So the example here is with redox reactions. It will be more favorable for certain compounds to lose electrons and for certain compounds to gain electrons. And so the transfer of those electrons can release energy. So chemical properties cause the release of energy from electron exchange of certain substrates, so elements or compounds. So you've seen, hopefully, a graph similar to this before, but I'll just draw it anyway. You'll start with your products having more potential energy that is released as when this reaction occurs. So this is where you start, and if this is where you end, then you have this much energy. So different substrates have different chemical properties, which means that some are more favorable to be oxidized or reduced. And we can actually quantify that. So that's E naught, or the standard reduction potential. That is the value that represents how likely something is to be reduced. So the standard reduction potential. We can say this is the tendency to accept electrons, being reduced. So some people get a little bit confused by this scale. So as we increase in value, we can be up to for example, positive 0.9. So this would be something like oxygen. This is our E naught. More likely to accept electrons than something on this end of the spectrum. Right? So because its reduction potential is higher, it's more likely to be reduced. So something that's less likely to be reduced, something that we see get oxidized pretty often, like glucose. We know that processing glucose, which is oxidizing it, releases energy. So it's more likely, instead of to get reduced and to accept electrons, it's more likely to donate electrons, getting oxidized. Oh, and actually for this class, since we're talking about biological organisms, E naught usually represents, in chemistry at a pretty strange pH. But since we're talking about life, we're going to talk only in terms of pH 7. So this, apostrophe here says, okay, we're going to be talking at a neutral pH. So if you're looking up values in a textbook or online or something, you're going to be using this marker to indicate I want pH 7. So if we have a redox reaction, we're going to write them as two separate half reactions. We're going to have an oxidation reaction and a reduction reaction. They're both half reactions. So say you have a compound that's getting oxidized. Its electrons are being taken away. So there are electrons that are being held between this hydrogen bond. So DH will turn into D plus this proton. So now this proton has lost electrons, and so we write electron, that makes up for the lost electron. And maybe it's reacting with another compound that's getting reduced. So we can say this compound A plus an electron plus a proton turns into AH. And the reason we have protons here is it helps us store electrons in bonds, because protons, hydrogen atoms, are often ionized into protons. It's pretty stable for them to be both in the ionized form and also in compounds. So if you put these half reactions together, you could make the whole reaction. So if we were to write both of these reactions with their arrow aligned, so we have DH turning into D plus H, or D plus a proton plus an electron. And then we have A plus E plus proton, electron, turning into AH. We can cross out the things that are on both sides. So if we were to average the reaction here, this is like Hess's law. If you know Hess's law, this is exactly like that. And also if you had 2DH goes to 2D plus 2 protons plus 2 electrons, you would want to multiply this reaction by 2 so that you have 2 electrons on both sides that you can cross out. So we can cross out the electrons and also the proton. And so what you're left with is A plus DH goes to D plus AH. Nice. And so this is your full reaction. These are your half reactions that you use to build it. So if you had a redox reaction you were trying to solve, you would want to, in a biological organism, most of the time you're creating energy. You're releasing energy through these redox reactions because you want to use them for, your anabolism. So if you're releasing energy, it's going to have to be a favorable reaction, which means that there's going to be a decrease in this graph here, which means you're going to have things that react the thing that is more likely to accept electrons will accept electrons for something that is more likely to donate electrons. So if you, this is often depicted as a table, which I'll show here. Something high up on the table wants to give its electrons. So it will, in a favorable reaction, react with something else on the table, and it will donate its electrons to something below it. So always the thing on the top of the table will donate its electrons to something below it. So if you wanted to quantify the energy being released from a reaction, you would calculate the delta E naught, which is just the standard reduction potential of the reduced compound minus the oxidized one, because if it's the reduction potential, this is the one that's going to be reduced. And the way that I think of this, which some people disagree with, is since this one is being oxidized, you flip the value. So it's kind of like you add them together, but this one is negative because it's not being reduced. This is the standard reduction potential, but it's not being reduced, it's being oxidized. So I think of it as adding these two values, but this one is a negative sign, like is multiplied by -1 because it's not being reduced. But you can also just think of it as the thing that's lower on the table subtracts the thing that's higher on the table. So this reaction is favorable whenever delta E naught is positive. So that what that means is the standard reduction potential of the thing that's getting reduced is greater than the thing that's being oxidized, which makes sense because it's getting reduced, so you want to reduce it. Which makes sense because if it's getting reduced, you want to be reducing the thing that is more favorable to get reduced. You have a reaction between hydrogen and oxygen, you're going to be making H2O. We can look at the standard reduction potentials of hydrogen and oxygen. So when two protons get reduced to be this dihydrogen, it will have a standard reduction potential of -0.42 volts. And that's a reaction that includes 2 electrons, right? Meanwhile, with oxygen, if you're making O2, when you reduce oxygen, you make water because it gets electrons from the protons you react with it. And that reduction releases 0.82 volts, and that's also 2 electrons. So this one, if you were to reduce hydrogen, oh, sorry, you can't really see. If you were to reduce hydrogen, it would cost you energy, like a volt, like, well, not a whole volt, but like almost half a volt. Whereas if you were to reduce oxygen, it's going to release 0.82 volts. So what you would want to do is you would want to reduce oxygen and oxidize hydrogen, because then when you oxidize, it's positive 0.42 volts. So the delta E naught here is 1.24 volts, because that's 0.82 plus 0.42. Or you can think of it as the E naught of the reduced, 0.82, is minus -0.42, which gives you the same answer. Okay, so let's look at all of these components together. So we're going to be reducing oxygen. So we have 1/2 O2, and if we're trying to make water here, it's going to be reacting with 2 protons. And then since we're deciding to oxidize this, we're going to be oxidizing H2. And then these and then since we're reducing, we're going to add the 2 electrons here. So what we're writing here is the thing that's getting reduced, the thing that's working with it, which is the protons, and then the electrons that are used in this reaction. So 2 electrons, and that goes into our other half reaction. So we have H2 turning into 2 protons, because remember we're going in the reverse direction because it's getting oxidized. Okay, and then if we think about this half reaction, this is getting oxidized, right? It's not getting reduced. So instead of looking at this side, we're going to look at this side, because the dihydrogen is going to be reduced, is going to be oxidized. So we have all of these components, and this will turn into our H2O. That's our oxygen, hydrogen, or that's our oxygen, protons, and electrons. And then this H2 will turn into 2 protons. And since we went in the reverse direction, the electrons are going to be on this side of the equation. Okay, so once again, we see things that are common on both sides, so we can go ahead and cross them out. So we can get rid of the 2 electrons and the 2 protons. And that gives you 1/2 O2 plus H2 turns into H2O. And so what we can do with this delta E naught is you can plug it into the equation for Gibbs free energy. So you have delta G naught prime equals negative n meaning moles of electrons, and then F, which is our Faraday constant, and delta E naught. So N is moles of electrons, F is our Faraday constant. Do we remember this from chemistry? So long ago. I did not remember this when we reviewed this. This is 96.5. But I remember now. Kilojoules per mole of electrons. So this is why we need to have N, is because it's over moles of electrons, and so we need to multiply by moles of electrons. This is a pretty important equation. Let's give it a shot. Let's see how we would use it on this formation of water. So delta G naught prime is equal to negative, and then the moles of electrons. So from that we have 2. So we have 2 mole E times the Faraday constant, which is 96.5 kilojoules per mole E. So this will cancel out. That's good. Multiplied by the delta E naught, which we found here was 1.24 volts. And that ends up giving you negative 239.3 kilojoules per reaction. So every time you do one of these reactions, you're going to be working with 2 moles of electrons, and that's going to give you this much energy. Nice. Okay, so here we're applying this equation. So we get energy from these reactions, but how do bacteria keep that energy? If they're not immediately applying it to a substrate, we're going to want to store it in some way. So how do bacteria store this energy from the redox reactions? Well, we should be pretty familiar reactions with these methods. So one is like ATP, high energy compounds. So ATP, think GTP and PEP, those are all things that we've used already that we know have energy. So it makes sense that these are ways we store energy. And then another one is the proton photoforce, which can be used to make these high energy compounds. Okay, so we can store this energy. So in catabolism, you learn electron shuttles. So our NAD and FAD. They transport high energy electrons from one compound to another. So let's talk about that a little bit more. So you have compounds like NAD plus, which is oxidized, right? It doesn't have many electrons because it has that positive charge, as compared to NADH, which has 2 more electrons, because there's the electron that would make this neutral, and then the electron you get from adding the proton. So this is reduced. So this compound, NADH, can go somewhere else in the cell and donate these high energy electrons. So electron shuttle can transport high energy electrons to power reactions. And we see that in an electron transport chain in something like photosynthesis. So you'll have something like your oxidized NAD plus an electron donor that'll give it electrons. And that'll turn into NADH and an oxidized product. So in the case of glycolysis, you'd have glucose here, and then you'd have your pyruvates. And this is facilitated by an enzyme. Obviously, it depends on what our electron donor is, what reaction is happening here, but it doesn't just happen on its own. There's an enzyme that facilitates it. And then same thing, you can have NADH plus an electron acceptor, and you'll go back to NAD plus and a reduced product. And these high energy electrons can power reactions such as the importation of a proton, if you're talking about like quinone. So this is also facilitated by an enzyme, albeit a different one. But as you can see here, since you need a reduced product to regenerate your NAD plus that you can use to take electrons and then oxidize something, and then, you need to have an electron acceptor. So when you're oxidizing some substrate, you can generate ATP through like the electron transport or proton motive force. But first, you need to go through an electron acceptor. So, and then you can make ATP. So there are a couple of different categories of electron acceptors. I feel like the very dominant one is oxygen, but that's aerobic. There are also anaerobic respiration systems. So you have atomic sulfur, you can have nitrate, you can have sulfate. And there's also organic electron acceptors. And so these are some options for aerobic respiration, but this is only in microbes. So everything other than a microbe is going to be using oxygen. And not all microbes are anaerobic, as we learned with our different categories. Like we learned about obligate aerobes, which need oxygen to, do things. Okay, so we can actually categorize organisms into where they get their electrons from and where they get their energy from. So if we talk about chemotrophs, chemo like chemical, they get their energy from chemicals. Makes sense. But where do they get their electrons from? Well, that depends. So we actually have two different categories. I'm going to draw it like this and like this. So we have chemo organotrophs, which the organo is they get their electrons from organic compounds. Whereas chemolithotrophs get their energy, their electrons from inorganics. So with chemoorganotrophs, they use an organic compound as both the electron donor and the carbon source. This is something that we do, we take a glucose molecule and we take the energy from it, and then we use the carbon atoms to make our biomolecules, and then that makes it like up our tissues or whatever. But with chemolithotrophs, since they get their electrons from inorganics, they're also getting their carbon from inorganics. So they do carbon fixation. Instead of just taking the carbon atoms from the thing that they're already breaking down like we do, they're not breaking things down like that. So they take CO2 from the atmosphere and do biosynthesis with that. Okay, so our two different categories are chemoorganotrophs. They take their electrons and their energy from chemicals and also their carbon. And chemolithotrophs get their energy from inorganics, but they still get their energy from chemicals. And they get their carbon from carbon fixation, atmospheric carbon. So if you want to get your energy from chemicals, where could you get it from? Well, have you ever heard of a plant? They're the ones that are making these higher energy chemicals a lot of the times that chemotrophs tend to be using. So photo, like light, they get their energy from light. Hooray. So once again, we're going to have two different categories here. So there are two types of phototrophs, and both of these get their energy from like either water or some reduced compound. Now we're not talking about their electron source, we're actually going to be talking about their carbon source. So photoheterotrophs get their carbon from organic compounds. I remember that because hetero is like different, and so it could be so many different organic compounds that photoheterotrophs use. And a photoautotroph, you think auto like self, it's making those organic compounds. So it is taking it, it's doing carbon fixation again, using CO2 in the atmosphere to make its own carbon molecules. Okay, so let's do a review. That's all we have for energetics today. Okay, we have our two forms of metabolism. We have catabolism and anabolism. Catabolism is producing energy by turning substrates into products. This is energy generation. And anabolism is using that energy, as you can see here, energy use, to do biosynthesis, make important compounds for the cell. Okay. So where does that energy come from that they're using in catabolism? These are all redox reactions. The chemical properties of different reactants will determine whether or not a reaction is favorable or not. And if it is favorable, then we can use this energy to power the reactions of biosynthesis. So chemical properties can cause the release of energy from electron exchange. And obviously, if you were trying to do it in the reverse direction, it would cost energy. But since that isn't favorable, it just doesn't happen very often. And we learned this term, which is the standard reduction potential. That's the tendency to accept electrons, the tendency to be reduced. And this prime apostrophe means at pH 7. So something with a very low value, especially in the negatives, is more likely to donate electrons. But when it increases, then it's more likely to accept electrons. Okay, so we have our oxidations and reduction half reactions, where we consider obviously our reactants, but also the electrons and the protons that are involved. And then we can use like the Hess's law kind of idea to balance that. And we can solve for delta E naught by subtracting the oxidized standard reduction potential from the reduced standard reduction potential, and that's favorable when it's positive, because that means the thing that wants to be oxidized is, and the thing that wants to be reduced is. And so we solved for that here by subtracting negative 0.42 from 8.82, and we used this formula to solve for delta G naught. And we found out that the way to store energy from redox reactions is in high energy compounds like our ATP, GTP, PEP, and our proton motive force. And then part 2, we talked about electron shuttles, which are really important in transferring these high energy electrons. So this is like FAD, NAD+. And it can oxidize things through enzyme-facilitated reactions. And substrates that have high energy electrons will give them to electron acceptors, and that will power like the proton motive force or the electron transport chain and make ATP. And so some of these electron acceptors, so our aerobic and anaerobic, oxygen is kind of the most common, but you can also see anaerobic things, but that's only in microbes. And then we talked about the ways that we can get all of this stuff. So we have chemotrophs, which get energy from chemicals, which includes chemoorganotrophs that get it from organic compounds, and that's also where they use their carbon source. And chemolithotrophs that get their electrons from inorganics, and they do carbon fixation because they don't have organic compounds to get their carbon from. So they have to use CO2 for biosynthesis. Kind of similar situation with the photoautotrophs, since they aren't using organic compounds like the photoheterotrophs, they have to do carbon fixation as well. And my marker's running out of ink, but hopefully that made sense. We're going to be talking more about energetics in the next episode 2. We're going to be talking about fermentation, so stay tuned. All right, bye.